Hello dears, how is your time going? This is Ethiopedia by Desu Birchit.
In this part and in the upcoming series, we are going to discuss matrix and determinants. As usual, we will start from the very basic and progressively move to solving some challenging questions as the installment continues. It's important to have a knowledge about matrix before discussing determinants. So let's start with what matrix mean. For better understanding about matrix, let's start with this hypothetical data in order to figure out from where matrices are derived from and their relation with real-life scenarios. Here it goes on. Addis Ababa Education Bureau collects the 4 consecutive years data about monthly school payment at 4 private high schools in the city. The payment in year for the years 2011 Ethiopian calendar to 2014 Ethiopian calendar is presented as hereunder. School 1, 1,800, 2,000, 1,300, and 2,500. School 2, 1,600, 1,850, 2,100, and 2,400. School 3, 2,100, 2,200, 2,500, and 2,900. School 4, 1,700, 2,050, 2,450, and 2,700. In order to present such statistical data in attractive, easily readable, and organized manner, tabular presentation is advisable. So let's transcribe this raw data into tabular form by constructing a table. In constructing the table, we can put the schools in rows and the academic years in columns or vice versa. For this case, let's put them as they are presented in the word problem, meaning the schools in row and academic years in column. Since each of the academic years and the schools are 4 in number, we can start the construction by drawing a table with 5 rows and 5 columns. That's just adding 1 to each of the total number of schools and the total number of columns for heading purpose. Let's write column headings as 2011, 2012, 2013, and 2014 in the first row starting from second column, and the row headings as SH1, SH2, SH3, and SH4 in the first column starting from row 2. SH is just to abbreviate the school. To clarify for what purpose the columns and the rows are standing for, let's add a merged row at the top and label it as academic year, and a merged column at the left and label it as payment in birth. Then let's copy the payment in each of the boxes in the table. This is a well-constructed, attractive, and easily readable statistical table. If we remove the headings of the row and columns, what we left with is a rectangular array of numbers arranged in different boxes. Again, if we get rid of a horizontal and vertical bars that separate the rows and columns, we will left with simple rectangular array of numbers. If we enclose this rectangular array of numbers in square or ordinary brackets, what we will find is a matrix. So let's define what matrix is. A matrix is simply a rectangular array of numbers arranged in rows and columns. Why it's rectangular array? Because it has a length dimension and the width dimension. The numbers inside the square bracket are called elements or entities of a matrix. In a given example, the numbers like 1,800, 2,000, 1,100, 2,900, etc. are elements or entities of a matrix. Since the elements are arranged in 4 rows and 4 columns, this matrix has a total of 16 elements, that's 4 times 4. The rectangular array of entities or elements are enclosed in an ordinary or square brackets. The reason for such enclosure is that it is a square or ordinary bracket that represents matrix symbolically. In a common notation, capital letter denotes a matrix, and the corresponding small letter with a double subscript describes an element of a matrix. For example, if capital letter A denotes a matrix, then the small letter a with the subscripts I, J describes elements of a matrix. We may ask a question from where these subscripts are derived from or for what they stand. The first subscript, that's I, stands for the row where the particular element is located, while the second subscript, that's J, stands for the column of that element. Meaning, the first subscript, that's I, is derived from the row, while the second subscript, that's J, derived from the column of a given element. Let me explain the importance of using both the row and column as a subscript. If we need to mention a unique element in the matrix, either we have to call it by its name or we have to mention its unique position by referring the row and column where that particular element is located. Using only a row or a column can't help us to pinpoint a particular element because both the row and column contains more than one element. For example, if I need to express this 1,100 in the form of A sub ij, I can't say A sub 1 given that subscript 1 is standing for the row, because row 1 contains not only 1800 but this 1800 and other 3 elements. Thus, when I say A sub 1, the audience can't understand which row 1 element I am referring about. If I say A sub 1 to mean that the element is located at row 1 and column 1, anyone can easily figure out that this element is 1800. That's why it's a must to use both the row and column as a subscript to pinpoint any particular element in the matrix. Let's illustrate on the above matrix in order to understand how the A sub ij of a matrix is denoted. Let a capital letter A is equal to a 4 by 4 matrix we formed. To represent each element in this matrix, we can use a small letter A and the subscripts I and j by referring the row and columns where this particular element is located. So let's start by forming a square bracket, which is used to represent matrix symbolically, and then continue to denote the individual element of matrix. The first element, that's 1800, is at row 1 and column 1 position. So it can be denoted as a small letter A sub 11. The first subscript stands for the row, and the second subscript stands for the column where 1800 is located. If we move to the right, we will find 2000, which is located at row 1 and column 2 position. So its A sub ij denotation is A sub 12. 1 stands for the row, and the second element, that's 2, stands for the column. 2300 is at row 1 and column 3 position. So its A sub ij denotation is A sub 13. 1 stands for the row, and 3 stands for the column where 2300 is located. Similarly, the A sub ij denotation of 2500 is A sub 14. The first subscript, that's 1, tells us that the element is located in row 1, and the second subscript, that's 4, tells us that the element is located in column 4. When we come to row 2, 1300 is located in row 2 and column 1 position. So its A sub ij denotation is A sub 21, meaning a certain element symbolized by A, and it is located in row 2 and column 1 position. The second entry of row 2, that's 1850, is specifically located at row 2 and column 2. So its A sub ij denotation is A sub 22. Second row and third column element, that's 2100, is denoted as A sub 23. This is to mean that the element is located at second row and third column. The ultimate elements of row 2 is positioned at row 2 and column 4. So its A sub ij representation is A sub 24. By the same token, row 3 elements are denoted as A sub 31 for row 3 and column 1 position, A sub 32 for row 3 and column 2 position, A sub 33 for row 3 and column 3 position, A sub 34 for row 3 and column 4 position. At last, row 4 elements are denoted as A sub 41, A sub 42, A sub 43, and A sub 44. As we go from left to right across a row, we find similar first subscript because we don't change the row, rather we move from one column to the next column in the same row. It's logical to expect the similarity because if we refer back the table from which the matrix is derived, a row represents 4 consecutive years monthly payment of a given school, meaning the row stands for the given school, but the columns in the row stand for the 4 academic years payment. On the other hand, we find similar second subscript when we move down a column because we are moving down from one row to another row in the same column. Again, it's sensible to encounter such similarity because a column stands for the monthly payment of a given academic year. For example, column 1 stands for the monthly payment of 2011 academic year, column 2 stands for 2012 academic year, and so on. Knowing this fact, let me introduce you one new concept about matrix, that is size or order of matrix. The size or order of matrix is M cross N, which is read as M by N, when M is the number of rows and N is the number of columns. In the matrix above, number of rows, which is M, is equal to 4, and number of columns, which is M, is equal to 4. Thus, M by N is equal to 4 by 4, meaning the matrix we have been referring is a 4 by 4 matrix. If we remove the fourth row, we will left with 3 rows and 4 columns. So the order of the matrix, that's M by N, becomes 3 by 4. It's simple to discern the order of a given matrix because what's expected from us is just to count the total number of rows and the total number of columns and then writing them in a form, the total number of rows, that's n, cross the total number of columns, that's n. Bear in mind, what's coming first is the total number of rows, and second is the total number of columns, but not vice versa. So far, we have seen how a given hypothetical data can be converted to matrix form and the different concepts about matrix. If we are given with matrix and for what it's referring about, we can figure out the different elements and their denotations. We can also convert them into tabular or some other forms of data. Let's see this matrix as an example. The matrix below represents the 4-week working hours of a company having 5 employees. In the given matrix, we have 4 rows and 5 columns. So we can easily figure out that the rows stand for weeks and the columns stand for employees. Because in the given example, we have 4 weeks, that's equal to 4 rows, and 5 employees, that's also equal to 5 columns. Assume the columns represent 5 employees designated as employee 1 to employee 5, and the rows represent 4 weeks of a month designated as week 1 to week 4. First question, what does A sub 44 tell us? It's given that column 1 to column 5 stand for employee 1 to employee 5 respectively, and row 1 to row 4 stand for week 1 to week 4 respectively. A sub 44 denotes 4th row and 4th column entry, that's 42.5. This 42.5 tells us that the 4th week working hours of employee 4, because row 4 represents week 4 and column 4 represents employee 4. Second question, which employee registered the maximum working hour? The maximum weekly working hour registered is 47. 2 elements are on tie with this maximum working hour. That's the element positioned at row 1 and column 5 and at row 3 and column 2 positions. So the maximum weekly working hour is registered by employee 2 in the 3rd week and employee 5 in the 1st week. This question signifies the importance of using rows and columns for referring a particular element. If you consider this 47, I can say employee 5 to mention the maximum weekly working hour because employee 5 registered 4 different working hours. Also, I can say week 1 because there are 5 different working hours in week 1. To be really specific, we have to mention both the rows and columns where that particular element is located, as we did employee 5 in the 1st week and employee 2 in the 3rd week. The 3rd question represents the matrix in table form. We can easily convert this matrix into tabular form just by removing the square bracket and adding the following. The first addition, a horizontal and vertical bars to separate rows and columns, and the second addition, the heading of each rows and columns. This table and the given matrix refer the same 4 weeks working hours of 5 employees. Hope you understand the relationship between matrix and data of real-life scenario. Finally, let's see how to construct a matrix if the individual element is given as a mathematical relationship between rows and columns. Here is the example. Construct a 4 by 5 matrix with capital letter A equal to A sub ij, where A sub ij is equal to 4 times the first element, that's I, minus 3 times the second element, that's j. We have 2 givens in this question. The first is the order of matrix, that's 4 by 5. As we have discussed, the first number, that's 4, stands for the total number of rows, and the second number, that's 5 in this case, stands for the total number of columns. So the matrix we are going to construct is the one with 4 rows and 5 columns. Let's start by forming a square bracket and then denote the 5 column and 4 row elements of a matrix in the form A sub ij. That's row 1 elements, A sub 1 1, A sub 1 2, A sub 1 3, A sub 1 4, and A sub 1 5. Row 2 elements, A sub 2 1, A sub 2 2, A sub 2 3, A sub 2 4, and A sub 2 5. Row 3 elements, A sub 3 1, A sub 3 2, A sub 3 3, A sub 3 4, and A sub 3 5. And row 4 elements, A sub 4 1, A sub 4 2, A sub 4 3, A sub 4 4, and A sub 4 5. Having this matrix, we can proceed to the second given. That's the mathematical relationship between an element of a matrix with the row and column where it's located. The relationship is already given as A sub ij is equal to 4i minus 3j, meaning every element is calculated by using the formula 4 times the row minus 3 times column where it is positioned. So let's proceed to the calculation. A sub 1 1 is located in row 1 and column 1, which means I is equal to 1 and j is equal to 1. Thus the calculation for A sub 1 1 position is 4 times 1 minus 3 times 1. For A sub 1 2 position, I is equal to 1 and j is equal to 2. So the calculation is 4 times I, that is 1, minus 3 times j, that's 2. For A sub 1 3, I is equal to 1 and j is equal to 3. So the calculation is 4 times 1 minus 3 times 3. For A sub 1 4, I is equal to 1 and j is equal to 4. Hence, 4 times I minus 3 times j is equal to 4 times 1 minus 3 times 4. Just substitute the value of I in place of I and the value of j in place of j. For A sub 1 5, I is equal to 1 and j is equal to 5. Thus, 4i minus 3j is equal to 4 times 1 minus 3 times 5. When we come to row 2, the first subscript, that is I, is equal to 2, and the second subscript, that's j, varies from 1 to 5. Thus, A sub ij is equal to 4i times 3j. For this row can be calculated as 4 times 2 minus 3 times 1 for row 2 and column 1 position, 4 times 2 minus 3 times 2 for row 2 and column 2 position, 4 times 2 minus 3 times 3 for row 2 and column 3 position, 4 times 2 minus 3 times 4 for row 2 and column 4 position, 4 times 2 minus 3 times 5 for row 2 and column 5 position. In similar manner, we can calculate row 3 and row 4 elements just by substituting the first subscript in place of I and the second subscript in place of j in the equation 4i minus 3j. At this stage, what we left with is simple multiplication and subtraction. That's in the first row, 4 times 1 is 4 and 3 times 1 is 3. Thus 4 minus 3 is equal to 1. For A sub 1 2 position, 4 times 1 is 4 and 3 times 2 is 6. Thus 4 minus 6 is equal to negative 2. For A sub 1 3 position, 4 times 1 is again 4 and 3 times 3 is 9. Thus 4 minus 9 is equal to
negative 5.
For A sub 1 4 position, 4 times 1 is again 4 and 3 times 4 is 12. Hence 4 minus 12 is equal to negative 8. And for A sub 1 5 position, 4 times 1 is again 4 and 3 times 5 is 15. Hence 4 minus 15 is equal to negative 11. When we come to row 2, 4 times 2 is 8 and 3 times 1 is 3. So 8 minus 3 is 5. 4 times 2 is again 8 and 3 times 2 is 6. So 8 minus 6 is equal to 2. 4 times 2 is again 8 and 3 times 3 is 9. Hence 8 minus 9 is equal to negative 1. 4 times 2 is again 8 and 3 times 4 is 12. Thus 8 minus 12 is equal to negative 4. 4 times 2 is again 8 and 3 times 2 is 15. So 8 minus 15 is equal to negative 7. In the same manner, we can calculate row 3 and row 4 elements and we will find these results. By this, I wrap up this section. See you later. Please subscribe, like and share this page. Bye bye.